recording?
Yes, yes, please start the recording. Yeah, thanks for reminding. So in this part, we will understand how to design system in a strategic environment. With performance guarantee. Now, let me explain these phases. What do you mean by strategic environment? It means that the players are strategic in nature. They are selfish. Their goal is to maximize their utility, and they can they are intelligent, so they have computational power. They can compute what is best for them. And and any such setting where the outcome or depends on the actions played by all the players is sort of, we will call, loosely system. Now this is sort of the broad goal of this week's lecture, and for concreteness I will take this auction as my system. And with respect to auctions, I'll explain what do I mean by having strategic environment and what are the performance guarantees and so on. So when I say auction, there can be multiple types of auctions. So in this course, we will focus on the simplest kind of auction, one of the simplest kind of auction that one can think of, what is called single item auction. Single item auction. So what is single item auction? There is one seller and one seller selling one item to n potential buyers. So all the theory that we study today also holds um, for the other setting where we have one buyer and n potential sellers. So an example of one seller and n potential buyer is, what is an example? So say government selling say spectrum or any resource. The seller is government, and maybe the mobile companies are the buyers, potential buyers. For the reverse setting, when we have one buyer and n potential sellers, the example could be, say, for an organization, IIT, say, wants to buy, say, certain kind of machine, and there can be n vendors, n possible vendors. From them, IIT can buy that machine. So, and there is only one item, not multiple items, only one item. Okay, so this is one. Second is, so we'll assume, so I'm explaining the setting of single item auction. What is the setting? Assume um, each buyer I in want to win, this set has a valuation Vi, which is a real number, positive real number, non-negative real number. It's a valuation for the item. So you can think of valuation as the maximum amount of money that the buyer is okay to spend to buy that item. That is valuation. And this Vi is known to buyer I only. Okay, so each buyer knows his private valuation for the item, which is not known to other players. And what is the utility? Utility of buyer I is 0 if he or she if he does not get the item, otherwise if buyer I gets the item, otherwise his utility is Vi minus P. If P is the payment, that buyer I. So sounds reasonable enough. The valuation for the item for buyer I is Vi. If he pays an amount P to get the item, then its utility is Vi minus P. Okay, so these are the players, this is the utility. And now still the auctions can be of many kind. Auction can be performed on many kinds, many types. For example, we have the most familiar ways of conducting an auction is that everyone sees the item in a hall and everyone makes a bid. So someone says say 100 rupees, then a countdown is made, and if there is someone who can bid more than 100 rupees, then he bids, and this goes on until there is no one who bids higher. So this is one possible way of conducting the auction. The other way could be the reverse. Maybe the seller announces that starts with a very high price, maybe 1 lakh rupees, and asks, is there any potential buyer? So if there is no potential buyer at that price, the seller reduces the price slightly and asks, is there any potential buyer? And this goes on until the seller finds a potential buyer. So these are the two familiar kind of auctions that we have seen most. But here we will assume something even more simpler, which is called sealed bid auction. Sealed bid auction. So single item sealed bid auction. What is sealed bid auction? That means here. So here is the first step. Each buyer submits his bid, his or her bid, in a sealed envelope. Okay, and then auctioneer then opens all the envelopes and decides who gets the good. the auctioneer after seeing all the bids decides the winner. Decides the winner. And the third step is payment. The auctioneer decides selling price. Selling price. Okay. So so here is the setting. So typically how the second step is implemented, all the bids are opened and whoever bids the highest is declared the winner. If there is any tie, there is some tie breaking rule, maybe like all lexicographic order of the names or something like that. Maybe randomly one of the highest bidder will be picked and decided as a winner. And the third step is typically implemented as the winner is asked to pay his or her own bid, right? And that is what is called first price auction. First price auction. Okay, so first price sealed bid auction is the winner is the highest bidder, and the winner pays his or her own bid, right? Winner is the highest bidder, and he or she pays his or her bid. Bid. Okay. Now it turns out that this first price auction is not so easy to reason about. Is right this way, hard to reason about. Hard to reason about. Hard to study. To reason about. What do you mean by that? Think of you being an and seller. You being a buyer. Now and you are strategic and intelligent. That means your goal in this auction is to maximize your payoff or your utility, which is Vi minus P. Now, how much you should bid? For example, will you bid your valuation? The answer is always no, because if you bid your valuation, then your utility is zero. If you win, your utility is zero. If you lose, your utility is zero. Sort of you do not want to. So it is sort of clear that bidding your valuation is as good as bidding zero or not participating in the auction at all. But then what will bid? What will you bid? So ideally, you would like to bid if in a hypothetical scenario where if you know all the bids of the bids of all other players, and the if the maximum bid of all other players is more than your valuation, then you definitely do not want to bid more than your valuation, because if you bid more than your valuation and by chance if you win, then your utility will be negative. So if the maximum bid among other players is less than your valuation, then you ideally would like to bid slightly higher a tiny higher than the highest bid of all the players. But the problem is that you do not know the bids of all the players. That's one. And not only you are the only one who is thinking this way or behaving strategically. So all the other players are also behaving strategically. They are participating in this game and their goal is to maximize their utility. Now you think about it and see that what will be, how much you will bid or what will be your bid is not an easy answer. So let me write. Not easy to decide how to bid or what to bid. Agreed? Feel free to unmute and speak if you do not agree with me or if you have any observation, any question or anything. You don't need to ask for my permission. You just unmute and speak. Okay. Now, if players, if the buyers, potential buyers, cannot decide what to bid, then think of the auctioneer or the player who is selling the item. Even if he knows the valuations of all the players in a hypothetical scenario, because in actually the valuation is a private information to the player only. So it is even harder for the seller to predict uh, the selling price. That means at what price eventually the item will be sold. Okay, so let's see another auction and see, we'll see that it has all these good properties. It does not have these bad properties, and that is called second price auction. Also called Vikri auction by the after the name of the inventor. So here again we are in a sealed bid scenario, sealed bid auction. There is only one item, one seller, n potential buyer. Everything remains same. I just need to decide the winner and the payment. Who will pay what? The winner is, as before, winner is highest bidder. Is a highest bidder. But the payment in the first price auction, the winner had to pay his or her bid. But in the second price auction, he or she does not need to pay his or her bid, and he may has to pay slightly less. So winner pays second highest bid. The second highest bid. What is second highest bid? You forget the winner, you remove the winner from this set and look at all other bids and take the maximum, because winner is the highest bidder. So the second highest bidder is the highest among all the non-winning buyers. So in particular, if there is more than one highest bidder, in that case only the winner has to pay his or her own bid, because after removing the winner, the highest bid among the remaining of the players still is the same as the bid of the winner. So in all other scenario, the winner has to pay slightly less. Now, is it easy to analyze this second price auction? For example, if you are a seller, so sorry, if suppose if you are a buyer, is it easy to decide how much to bid? Anyone? Not if any one of you is part of my game theory course or have taken game theory course, please don't answer. So how much the buyers will bid? Anyone? And here is the theorem. In second price auction, bidding valuations maximizes utility. Utility of the players. That means what? If you are a player, you simply bid your valuation. Player know his or her valuation, VI, and you simply bid your valuation. And we'll prove why this particular strategy, bidding your valuation, always maximizes the utility of the player. So such a strategy is called a dominant strategy. Is called a dominant strategy. In some sense, this particular strategy of bidding valuation dominates all other possible strategies. So for example, one strategy could be that you bid half of your valuation or something like that. You can think of various kinds of crazy strategies, and this particular strategy dominates all other strategies, in the sense that if you follow this strategy, your utility will be maximum possible. Question on the statement of the theorem. Is the statement of the theorem clear? And this is what we mean by it is very easy very easy to analyze this sort of auction, second price auction, because see now see the life of the potential buyers. They don't have to think of anything crazy. They know that if they bid simply their valuation, their utility will be maximized. So they simply bid their valuation, and the auctioneer, the seller, also knows this fact, and hence the seller also knows that all the buyers will bid their valuations, and if and the seller has some pre-knowledge or some prior over the possible valuations, then the seller also has some knowledge about how much money the seller will receive or how the system will behave. That is what we mean by the second price auction is much easier to reason about. Okay, question about the statement of the theorem before I prove this. Okay, so let's prove it. So let I be any player. What I will show is that bidding the value, its valuation Vi will maximize his or her utility. Okay, so let B be the highest bid among the remaining players. Okay, what do you mean by remaining players? You delete I for the time being and look at the bids of all the other players, and suppose B is the highest bid. Okay. Now and let Bi is the bid of I. We will show that setting Vi equal to Vi maximizes the utility of the player I. So if Bi, there are two cases. If Bi is less than B, that means player I's bid is not the highest bid, then player I loses, and then utility of player I is 0. On the other hand, if Bi is greater than equal to B, assume that tie breaking tie is broken in favor of B. Say, then player I wins. Player I wins, and his utility is valuation minus how much is the payment? Payment is B, capital B. This is utility. Okay. Now we will show that this is setting Vi equal to Vi is or guarantee that highest utility is achieved. So consider two cases. First case is if Vi is less than B. That means if the valuation, so when we are arguing about player I, we're sort of keeping all the other players fixed. They are not changing their bids. Now, if Vi is strictly less than B, that means player I's valuation is strictly less than the highest bid among other players. Then in that scenario, is it a good strategy for player I to bid higher and win? No, the highest, in this case, the highest possible utility possible utility for player I is what? If it wins, then its utility is 0. And if it loses, its utility is Vi minus B. And if I take max, this is 0. Now, in this case, when Vi is less than B, if it bids, if Bi equal to Vi, then it loses and it receives its highest possible utility, which is 0. Let's see the other case. If Vi is greater than B, the highest possible utility is greater than equal to highest possible utility for player I is max of, again, if it loses, its utility is 0. If it wins, its utility is Vi minus B. But in this case, Vi is greater than equal to B, so max is Vi minus B. Now see, if Bi equal to Vi, then Bi is also greater than equal to B, and in this case, his utility is Vi minus B, the maximum attainable utility. Hence, irrespective of how other players bids, whether they bid their valuations or not, it does not matter to player I. Irrespective of how other players participate in the auction, it is always in the best interest of each player to bid the valuation. This is what we call dominant strategy incentive compatible, or or forget that. So as we are saying that here, it is much easier for the players, for the buyers, to participate in the auction. Okay, questions? Okay. So this is sort of one simple scenario where we have observed that there are many things to design in auction, and now we'll see a more broader case, not only the sealed bid auction. So, but before that, let me write down theorem of Vickrey without proof. At Vickrey auction, satisfies the following. Following properties. The first property is that, as what we have just proved, is that bidding valuation always maximizes the utility, and this is called in game theoretic term that it is dominant strategy incentive compatible. It is dominant strategy incentive compatible. Dominant strategy incentive compatible. DSIC for short. Whenever in an auction scenario, the best strategy of the players is to report truthfully or participate truthfully in the system. Such a system we call it a dominant strategy. Such a system we call dominant strategy incentive compatible. So whenever a system is dominant strategy incentive compatible, such system is very easy to reason about. It is very easy to predict for players. It is very easy to participate in the in such a system, and for system designer also, it is much easier to argue or predict how the system will behave. The second one is that you see that because each player bids his valuation, so from the bids of all the players, the true valuations of all the players becomes known, which was the valuation. Recall, the valuation of player I, which is Vi, was known to player I only, But because of DSIC property, after the auction is over, the valuation of all the players becomes common knowledge. Second one is performance guarantee. That if, right this way, if bidders report truthfully means they bid their valuations, then the auction maximizes the social surplus. What is this? Surplus. What is social surplus? This particular quantity. I equal to 1 to n vi xi, where xi is 1 if player I wins and gets the item and 0 otherwise. And vi is the valuation of player I. Now you see that in the second price auction, because it is DSIC, players bids truthfully vi, and the item gets allocated to the highest bidder. So the allocation, that means the rule which decides who will get the item and who will be the winner, that particular rule maximizes this particular summation, which is called social surplus. In many applications of auction, it is not maximizing revenue, maximizing the amount of money that seller receives is sometimes not the primary goal. It's sometimes a secondary goal, and the primary goal is sometimes in those cases is to give the item to the player who values that item the most. And this sort of scenario is typical in auctioning government properties or something. For example, government is auctioning some natural resource or something, say spectrum, among n potential buyers, and the goal of the government is to give or allocate that particular natural resource or spectrum, for concreteness, to that particular player who values this particular object most. And now, see the difficulty, if you simply ask the players, you tell me how much you will value, because the players are strategic in nature, they may not tell the truth. And that's where this sort of intelligent system design comes into picture. Can you come up with an auction, in this case auction, where it is in the best interest of the players to report truthfully, and the government or the auctioneer can allocate the item to the highest possible bidder. And the third one
What is
is,
XI?
yes, xi is allocation vector. Xi is 1 if I wins and 0 otherwise. So if I wins and gets the item, then value of xi is 1, otherwise it is 0. Okay, and then the third property is computational efficient. You can design an awesome auction, but if it is so computationally heavy that to decide a winner, it takes 1 year of computation in the supercomputer, then it is not worthy. So computational efficiency is also important. And as you can see here, the rule for deciding the winner and the rule for deciding who will pay how much is so simple, that it can be implemented in linear time. You just simply read, and this is computationally very efficient. So the auction can be implemented in polynomial time. In fact, it in linear time, polynomial time. Okay, so these are the properties of wiki auction. Now let's see for concreteness some other kinds of action, some other kinds of auction. So the first one, and we'll see a DSIC auction for this particular setting also, which is called sponsored search auction. Okay, so what is the model? The model is that whenever we search something, search for a keyword in any search engine, say Google, here is the keyword, and then we get these results. And on the right hand side, here we see various ads, ad 1, ad 2, so on. Sometimes here also there are some ads. So what I'm saying is that for a keyword, there are some predefined space in this in the window which are allotted for showing ads. They are not for the results. The results, actual search results, are here. Now here, which ads to show for which keyword? It's not like that that some ads are predefined that it will be shown in this particular slot irrespective of the keyword. It depends on the keyword, because from the keyword one can, or the system can understand what is in the user's mind, and it will show only those kinds of ads. But then what kinds of ads to show? And there, as you can see, there are multiple slots. It's not like single item sealed bid auction. There are multiple slots, and the question becomes which ads to show in what slot. And to decide that, some kind of auction is again conducted, and that is called sponsored search auction. And see here the computational requirement, the which ads to be shown to which slots, that must be computed in the time from the user will type the keyword, and within seconds, within fraction of seconds, the results will come. Within that time, you have to compute, the system has to compute or decide which ads to show which slots. And it turns out that in 2006, Google used to earn 98% of its revenue from sponsored search auction. So this shows how important for a company like Google to show the right ads at right places for right keywords. Okay, and the payment mechanism is typically this, that if the user does not click on the ad, Google does not get any money. On the other hand, if user clicks on some ad, then that particular hyperlink opens in a tab, and then Google receives certain amount. So it is absolutely must. It is absolute must for the Google to show the right ads at the right place for the right keywords. Okay, and typically from history, for a fix a keyword, so there is something called click-through rate. So suppose there are k possible ads which are fighting for these slots, and Google has this data which is called click-through rate. CTR. In short, CTR. Suppose I have K slots. Say this is add 1. Suppose this is add 2, add 3. This is add K. There are K slots. That means K ads can be shown. And because of natural behavior of the browser, that it scrolls from top to bottom, the ads shown at the top of the page is more likely to get clicked than ads shown at the bottom. So suppose this is the probability with which this particular ad is clicked, alpha 1, alpha 2, and so on. So this particular information is typically available from historical data. So alpha 1 is greater than equal to alpha 2, and so on. This is greater than equal to alpha k. Okay. So this depends on this sort of encodes the goodness of the position. From the position itself, irrespective of the ad, how likely the user clicks on the ad. And the other one is for each advertiser. Each advertiser say I has a quality score which is say beta I. That means, okay, so for each ad, it is assumed that whether it is clicked or not, it will depend on two things. One is the quality of that ad. How good is that ad? And second is where it is shown, in which slot. So the slot, the probability for those slots is alpha 1 to alpha k, and the goodness of the advertiser is encoded with this quality score beta I. And here is the assumption, that if ad I is shown in slot J, then it is clicked with probability beta I times alpha J. Okay, and here also the same sort of thing, that Google runs an auction, and here the Google's or the auctioneer's goal is to again maximize the revenue and yeah, maximize the revenue. And of course, it is not a sealed bid auction. And in maybe next class, we'll see how to design the allocation rule and payment rules for these auctions. Okay. Questions. For example, the most natural one would be that you sort all the available ads with this quantity and take the top K. But that sort of thing does not work, because if some ad has very high beta I, then you do not want to show the same ad in two different slots. So you want to show K different ads in K different slots. Then you can say that, okay, you take the top K, but don't repeat the ad. But that is not DSIC, and that does not maximize the revenue also. So how to design such or more complicated this sort of auctions, we'll see coming lectures. Okay, questions. So I'll post the lecture video from where I'm covering this content. I'll share with the TS, and TS will post it. Okay, questions. Okay, so if there is no question, so let me stop here. We'll meet in the next class.